So, good morning. For some of you, it's going to be good afternoon. It's my pleasure to open a series of CINE Webinar. So today is our first webinar. We have Professor James Durrant as the first speaker, Professor James from the Imperial College. So I am Ana Flávia Nogueira. I am one of the principal investigators of CINE, the Center for Innovation on New Energies. So before calling James to our studio, I'd like to give you some information. So this webinar is being broadcasting through YouTube, and you can ask James questions when as soon as I open the session for questions. You can send your questions by using the chat in YouTube. So please also include your name and the name of your institution. Okay, we are going to try to answer all the questions, so depends on the time. So, okay, let me introduce welcome to Professor James Durrant, that is also a member of our International Advisory Board. So, James, thank you very much for accepting our invitation to open this series of webinar from CINE. It's a great pleasure to have you here. So let me say some few words about James. James is professor in the chemistry department in Imperial College, and also professor in the engineering department in Swansea University. But James is a physicist. James is a long friend of mine. I was with James during my PhD, and also I was with James. I was postdoc in his group, working on starting the work on the OPV, studying charge recombination of PV, long time ago. So since then, James has visited Brazil many times. So James, it's a pleasure to have you here. James is an expert in the field of photochemistry. It's an impressive curriculum. So James received many honors, many prizes, has more than 500 papers published, age factor of 400. So a very impressive curriculum. It's an honor for us to have you here, and we are looking for your talk.
Thank you very much, Anna. That's very kind. It's a real pleasure and an honor to be giving this first webinar of the CINE Center. I'm very sorry I haven't been able to join you in person in CINE so far, but I'm looking very much forwards to joining you as soon as travel allows. What I thought I'd try and do today was talk through the challenge of the solar-driven synthesis of fuels and chemicals. I'm primarily a photochemist. Originally I was a physicist, as Anna said, but really now I'm a photochemist. And what I want to talk to you about is some of the photochemical challenges associated with using sunlight to make fuels. And of course, to make a fuel, we have to think about catalysis. So I'll be talking about the connections between photochemistry and catalysis. First of all, I'll briefly introduce the center I lead at Imperial College, the center, what is called now the Center for Processable Electronics, the CPE. I'll just touch on that, and certainly one of the motivations for my engagement with CINE is to think about the opportunities for wider collaborations between the CPE and CINE. I'll then go on to talk about the motivation and the challenge of solar to fuels, about why it's interesting and what are the key difficulties in trying to achieve the solar-driven synthesis of fuels. And then I'm going to go on to really the core science of what I find interesting. I'll be talking about kinetics, and particularly around how we need to gain lifetime to drive catalysis. And so that's about the idea the initially generated states are short-lived and the catalysis is slow. And then the last part of my talk, I'll get into the real more detail on the catalysis, and particularly thinking about how we can use spectroscopy to measure the kinetics of catalysis, and particularly looking at water oxidation, which is maybe one of the most challenging reactions in the solar-driven conversion of sunlight to fuel. So the CPE, it's a center at Imperial College. We're just looking at the science and engineering of scalable electronic materials. And so it was set up originally to look at semiconducting polymers, the ability to print semiconductor inks using conjugated polymer chains. It's now broadened to include inorganic and hybrid materials, and its focus is on particularly materials and devices for application in sustainable energy in soft electronics, where the word soft implies materials which are relatively soft molecularly and so respond to the movement of charge, and of course other associated technologies. In terms of this particular link with CINE, then of course the theme of sustainable energy is maybe the most relevant, and we have a large program in the CPE looking at across a spectrum of materials and devices which can be applied to sustainable energy technologies. Particularly today, I'll be talking around the area of solar diffuels and photoelectrocatalysis, but we have wider interest in solar cells and lighting and displays. In terms of what we do, then of course we're interested primarily in the transition between a material to a device, and so we're particularly focused on the synthesis and the characterization and modeling. It's the characterization, trying to understand function, and particularly using spectroscopy to understand function, which is what I'm going to be talking about today as my own particular research interest. Now, if we think, can I move that out of the way? If you think about the challenge of converting sunlight, of harnessing sunlight, then of course there are two well-established pathways to do this. The most established pathway is plant photosynthesis, which of course harnesses sunlight to drive the synthesis of biomass, as I'll talk about more just briefly in a minute. Then of course we have solar cells, and the most obvious solar cells of course are the silicon solar cells, which are now becoming so widespread around the globe. My own interest is in some of the newer technologies such as organics and perovskites, but these are two alternative and well-established approaches to harnessing sunlight. I'm going to talk mainly today about an alternative approach, what is often called artificial photosynthesis. So again, it's based primarily on inorganic, sometimes molecular materials, which are not natural but are made in the lab. But the aim of this approach is essentially to, following the inspiration of nature, to harness sunlight to store the energy in chemical bonds. So the drivers for trying to develop artificial photosynthetic systems, the first is the idea that we want to be able to move away from fossil fuels to sustainable fuels, to fuels which don't require CO2 emission, or at least in the net cycle of use. In addition, of course, we're interested in developing sustainable chemicals. Many of the chemicals used in the chemical industry derive from fossil fuels. We're interested in being able to take CO2 from the atmosphere and trap that in chemicals or using sunlight. The other challenge is that solar energy as we move to an energy technologies which are more reliant on solar as an input, then we have to be concerned with the fact that both solar energy is intermittent and it's localized. In particular, we have the issue that we need to keep the lights on when the sun goes down. But maybe more importantly, we need to think about how we're going to move the energy from sunlight around the globe, because there's a large mismatch between the sunniest parts of the world and the parts of the world with the highest energy density. And this is the idea you could see at the bottom of this picture, the idea of liquid sunshine. If we can use sunlight to convert CO2 and water into some sort of molecular fuel, then that's a relatively elegant and well-established way of moving large amounts of energy around the globe. The last motivation is around the challenge of CO2 utilization. There's lots of interest now in trying to develop CO2 chemistry, and there's many ways to do this. One way is to directly reduce CO2. Another way is via green hydrogen, and indeed there's an increasing interest globally in using hydrogen as an energy vector. But of course, currently almost all the hydrogen we use is derived from fossil fuels and releases CO2 at the point of generation. And the motivation here is to try and have green CO2 where there's no CO2 released, or at least a minimal amount of CO2 released during generation. Now, when we think about the challenge of taking sunlight, water and CO2 and making fuels, then this is already possible. You can take solar cells and you can make electrons. You can take electrons and you can electrolyze water to hydrogen, and you can take hydrogen and react it with CO2 to make a hydrocarbon fuel. And so there are already technology pathways which make this possible. Of course, the challenge is that currently both the green hydrogen produced by these routes or the chemicals made by the full route going down to the carbon-based chemicals, these pathways are currently too expensive to compete with hydrogen or chemicals derived directly from fossil fuels. And so the challenge is to do the science to enable us to get from here and down to hydrogen or down to carbon-based fuels more cheaply and, of course, scalably. There are many pathways to do that. One pathway is to make solar cells and electrolyzers and thermochemical reduction of CO2 cheaper and more energy efficient. What I'm going to be talking today is about an alternative pathway, which is where we can try and integrate some of these steps into a single process. And in particular, I'm going to talk about the potential of using sunlight to split water into hydrogen and oxygen. This is sometimes called converting sunlight, and so, for example, Mission Innovation, which is the global consortium looking at technologies which may impact our CO2 emissions going forwards. This is the focus of this sunlight conversion challenge. It's also the focus, for example, of the solar fuels network we've set up in the UK. And so I'm going to be focusing particularly on the challenge of harnessing sunlight to split water into hydrogen and oxygen. And I know, of course, this is already an area of interest within CINE. So when we think about how you can split water into hydrogen and oxygen, then there are many possible ways we can configure materials and devices to do this. Here are 3 illustrations. Of course, you can take a solar cell and couple that to catalysts, and either of these catalysts can be directly put on the solar cell in this artificial leaf, and this demonstrated by Dan Nacera, or you can have the electrocatalyst separately from the photovoltaic device. But you can also envisage examples, for example here, where you have a photoelectrode, where you shine light on that photoelectrode that makes electrons and holes, and those holes, for example, in this case, go on to drive water oxidation to give you molecular oxygen, whilst the electrons go on to reduce protons to hydrogen. And finally, you can have an example where you don't have electrodes at all. You don't have wires. You just have, for example, a suspension of particles in water. You shine light on those particles. You make electrons and holes, and those electrons and holes, in principle, can drive the desired chemistries. Now, in principle, this particle suspension route, most estimates suggest this could be the cheapest way to make hydrogen from sunlight. It's also currently the least efficient. And essentially it's inefficient because these electrons and holes tend to recombine rather than driving this chemistry. And so we need to understand what makes electrons and holes recombine rather than driving the chemistry, and that of course is around kinetics, and what I'll be talking about today. And indeed, the kinetics in these particle suspensions are essentially the same kinetics as in these photoelectrodes. These photoelectrodes have the advantage, but if it doesn't work very well, you can add a battery to make sure it does work. That, of course, or a photovoltaic cell outside the system, if you wished, to provide an additional voltage. That makes it easy to make it work. It's, of course, less desirable as a technology, but it makes it rather useful in terms of studying in the lab. In terms of materials, then there are many materials which have the potential to contribute to any of these technologies. If we think about the particle suspensions and the photoelectrodes in particular, then the classic sorts of materials are nanostructured metal oxides. Metal oxides are particularly interesting for water oxidation because they're stable to oxidation. Water is quite hard to oxidize, and so you need something which is resistant to oxidation to drive the chemistry. And metal oxides are one of the most stable things to oxidation. But you can also imagine buried junctions. This is an example of a buried junction where an organic bulk heterojunction is being used to separate electrons and holes, in this case the electrons, to drive the proton reduction. And then, of course, in addition to the semiconductor, you need catalysts, because the reactions are quite complicated. The 2-electron reduction of protons to hydrogen, or the 4-hole oxidation of water to molecular oxygen. And those catalysts can either be inorganic, and here's an example of a cobalt oxide analog developed by Dan Nacera, or they can be molecular, and this is a molecular catalyst developed by Li Cheng Sun. In both cases, the catalysts are there for these catalysts to drive water oxidation. Now, in terms of understanding the kinetic challenge, well, I've always found it helpful to first of all consider how plants are able to harness sunlight to drive the synthesis of biomass. And of course, plants, photosynthesis of plants happens in leaves, it happens inside the photosystems in leaves, and in particular it's based upon the idea that sunlight comes into a primary donor, it excites this primary donor, that initiates a series of electron transfer events which separates electrons on one side of the membrane and holes on the other side. The holes, in this case it's at PS2, the holes directly oxidize water, the electrons go on via a relatively complex chain ultimately to reduce CO2. Now, in terms of the efficiency by which plants harness sunlight, then at a molecular scale, if we look at the scale not of making biomass, but of storing the energy in chemical bonds, plants can be remarkably efficient. Under optimum conditions, plants can convert sunlight to chemical energy at an efficiency of around about 20%. If you look overall at making biomass, then it goes down to around 13%. But of course, glucose down to 13%. But if you actually look overall at the organism, how much the organism is able to convert sunlight into biomass, then whilst there are plants, and one of the most obvious examples, a famous example, is sugarcane in your own country, Brazil, which is efficiency significantly higher than 1%. But most plants convert sunlight to fuel at rather less than 1%, and certainly much less than a silicon solar cell. And this, of course, is the challenge. For biomass is fantastic, it's important, but overall biological conversion efficiencies are nowhere near as high as a silicon solar cell. And in addition, as we move towards more reliance on bioenergy, then we already are finding there's issues of competition for arable land for food production versus bioenergy and biomass production. So that's not the point of the talk today. However, the point here is that it is possible to harness sunlight to drive the formation of chemical bonds at remarkably high efficiencies. And that, of course, is the inspiration for much of what I'll be talking about today. In terms of how it works, then there's particularly a lifetime challenge, which I find interesting. When you absorb a photon by chlorophyll, the lifetime is nanoseconds. If you want to drive catalysis, and for example, the catalysis of water oxidation, then the lifetime is milliseconds to seconds of those catalytic centers. And so you have a challenge. You have excited states living for nanoseconds, and you want to drive chemistry on the millisecond to second timescale. Plants do this by separating the charges, as I described, and they separate the charges to gain lifetime, because if the charges are separated apart, then they'll take a longer time to recombine. But of course, that separation of charge costs energy. The energy of the separated states driving the chemistry in plants is around half the energy of an initially generated excited state. So the plants lose around half the energy from the sun in driving the reactions, which enable the carrier lifetimes to be long enough to drive the catalysis. And that's an interesting challenge, because it suggests that you need to gain lifetime to drive catalysis, but that costs energy. And that reduces efficiency. And we've been trying to understand essentially that argument in many systems in my group over the last few years. This is just some examples both from dye-sensitized and organic solar cells and what I'll be talking about today, water photoelectrolysis. And in both cases, there's a large lifetime gain required in solar cells not to drive catalysis, but to drive the extraction of charge to the external circuit. In the water photolysis, it should drive the catalysis. The lifetime gain is most challenging for the catalysis because it's so slow, and that correlates with the observation that these energy losses are the energy losses typical in the best devices. And you can see that for water photoelectrolysis typically has a larger energy loss, and that's probably correlated with having a larger lifetime gain required to drive function. Another way of drawing this is to look at the energy loss between the photon excited and the energy of the product versus how long it has to live to drive chemistry or to drive function. And you can see that here's perovskite cells and gallium arsenide down here have a small energy loss and very rapid extraction of charge to the external circuit. Here's photosynthesis, here's dye cells, and here are metal oxides trying to oxidize water. And you can see the lifetime gain of the lifetime required to drive the catalysis is slow, and the energy loss is large. And so much of my talk is around this kinetic challenge, how we can understand it, and how we can try to think about making it less severe. Another way of saying that is if you plot the performance metric for a photoanode, and this is a typical data for hematite from Michael Gratzel, and this is pretty much state of the art. That this is the current voltage curve for oxidizing water on a hematite photoanode. In the dark, you have to apply a large potential, large compared to 1.23, which of course is the equilibrium potential for splitting water. And in the dark, you have to apply a large overpotential to drive water oxidation on hematite. In the light, you have to apply much less potential. So this, if you like, is photo-assisted electrolysis of water. And you can see there's a turn-on curve here, which corresponds to the turn-on of water oxidation at a certain potential in the light. But if you could, and essentially, you need to apply a potential positive flat band, where flat band it corresponds to when there's no band bending at the surface. But in principle, if you could apply a potential of 0.5 volts, you turn on the band bending at the surface, and you absorb enough photons by hematite to generate 12.5 milliamps per square centimeter of current. And so that would be the ideal current voltage curve for hematite. This is where we are. This is where we'd like to be. And essentially, why we are here and not here is recombination. It's this kinetic challenge which I want to talk about today. If we look a little more detail about what's going on, then of course, when we absorb a photon by a metal oxide, you generate electrons and holes. What you want is the hole to go to the surface and to drive the chemistry. But in practice, what happens is the hole recombines with electrons, either in the bulk or on the surface. We also have to worry that many of the materials we talk about are defective and lots of traps, and this can indeed also mediate recombination. And so it's trying to understand these kinetic challenges. So what I'll be talking about today. And the way we do that is with spectroscopy, and particularly operando spectroscopy. And so we would take our material of interest, we put it in water and apply a potential to it, we shine light on it, and we try and measure the kinetics of electrons and holes by measuring their absorption, the changing color of the sample due to generating these carriers, and we measure that as a function of time after excitation. And so you can see some optical signal as a function of time, which gives you an idea of how long-lived holes or electrons live in the material, and there you use that to try and understand function. To give you another way of thinking about the kinetic challenge, then this just illustrates the idea that the charges are generated on very fast timescales, the catalysis is slow, and between those two timescales there's many loss pathways, traps, and surface states, bulk recombination. All of these processes on timescales going from picoseconds to milliseconds mean that most of the carriers which are generated by the light do not drive catalysis. And that, of course, is the challenge. If we start to actually drill down now to real data, and this just gives an example of kinetics for three oxides, hematite, bismuth vanadate, and titanium. On the left, we have plots of the optical signal of the charges as a function of time on very fast time scales. This is a log time scale going from a picosecond out to a few nanoseconds. And the decay is essentially because this is a bulk material. These are the decay of the bulk charges in those materials. And you can see that the charges generated in these oxides don't live very long. Titanium is reasonably good. The carriers live for a few nanoseconds. For hematite, carriers live for a few picoseconds before they recombine. Those fast timescales are important when we compare them to catalysis. So these are timescales of catalysis. Catalysis is a little hard to quantify timescales. What we've plotted here, and I'll come to later, is a plot of a turnover frequency, so 1 over lifetime, versus the amount of holes on the surface. The point here is that these numbers here are timescales of the order of 1 or 10 per second. So the order of a second or 100 milliseconds for reaction times. You can see the reaction times vary with hole density. I'll come to that later. And that, of course, is an illustration of a kinetic challenge between picoseconds to nanoseconds here and hundreds of milliseconds to seconds here. It's also obvious that the kinetic challenge varies between oxide. So hematite has the fastest bulk decay times and the slowest water oxidation compared to the other materials. And that's essentially why hematite in principle is a fantastic material. It's very cheap, it's very stable, and it absorbs lots of sunlight compared to bismuth or titania. However, the kinetic challenge for hematite is far worse than either bismuth or titania, because you have to gain more lifetime to drive function. And that is essentially why, whilst hematite has all these good properties, the kinetics mean that ultimately it is not such an easy material to make it as an efficient photoanode for water splitting. Now, how do we gain lifetime? By far the easiest way to gain lifetime is to introduce band bending. If you apply a positive potential, then you generate a space charge layer, just as a space charge layer in the PN junction of a silicon solar cell. And that space charge layer has fields which drive holes to the surface and electrons to the bulk. And you can see that experimentally. But if you apply a positive potential to hematite and look on long time scales, this is time scales of microseconds to seconds, potentials which are not very positive, you just have a small decay of trapped charge in the hematite. But as you apply a more positive potential, you generate the band bending, you drive the holes to the surface, the electrons to the bulk, and now you gain lifetime. And you can see that in particular, you can generate this very slow decay phase of a decay time of around about a second, which are the holes getting to the surface and driving for water oxidation. And indeed, the amplitude of this slow decay phase correlates rather well with the current you measure as a function of voltage. But applying a voltage to gain lifetime is an energy input. You don't want to have to do it, because whenever you apply a voltage, that voltage has to come from somewhere, especially if current's flowing through it, and so that costs you energy. So of course, there's a huge amount of research trying to think of approaches to gaining lifetime without applying a voltage. And you can see 3 examples there. These are all examples around making junctions. Essentially, it's the same idea as in photosynthesis, or it's the same idea as the junction between a dye and titanium in a dye cell, or the donor and acceptor in an organic solar cell. These are approaches where you separate the charge across an interface. In this case, on the left, is separating charge by putting a molecular catalyst on the surface. And the more you move the molecular catalyst away from the surface, the longer the lifetime is for the recombination, which means you gain more lifetime if you move the charge further from the surface. This is an example of a particle where simply by putting a silver nanoparticle on the surface of titania, you turn the lifetimes of generated carriers, and this is for just titania by itself. Almost all the carriers are disappeared by a few microseconds. When you put silver on the surface, the holes in titania live for almost a second. And this is because the holes live in a second down here. The electrons go to the silver nanoparticle. You get a spatial separation of charge, which gains the lifetime, which allows you to turn on, in this case, the oxidation of water and the reduction of CO2 to methane. Another particularly controversial example is when you put co-catalysts on the surface of hematite. And so in this case, we're putting cobalt phosphate on the surface of hematite. And what you observe is you don't need so much voltage to drive the water oxidation. And we observe that the carrier lifetimes, just measured with no bias, get much longer, just by putting the layer on the surface. Part of this lifetime gain is because you actually create a Schottky junction between the rather metallic catalyst and the semiconductor, which increases band bending. Sometimes, and in some cases, you get a gain in lifetime because the holes directly transfer to the catalyst and then go on to drive auto oxidation from the catalyst itself. So those are all approaches which are interesting to gain lifetime without requiring so much voltage input. Now, in terms of thinking about the materials, then one of the biggest challenges of oxides is they're full of defects. And you can see some examples of this here, that oxides have deep traps, they have shallow traps, and many of the materials which we're interested in have defect states. We're interested in materials which are highly scalable, highly processable, which don't have large embedded energies in their fabrication. And these tend to be more defective materials. Now, the role of states within the band gap in function is quite controversial. Because, of course, one strategy to make materials better is to dope them. When you dope a material, you introduce states in the band gap. Another strategy to make some materials more light absorbing is, again, to introduce states in the band gap to lower the optical band gap of a material. On the downside, of course, states in the band gap can act as traps and accelerate recombination. And so trying to understand the impact of defect states on device performance is quite challenging and interesting. And in particular for oxides, oxygen vacancies are by far the most interesting and wide, or certainly the most prevalent defect in metal oxides. Many oxides tend to be substoichiometric in oxygen, which is why most oxides are N-type. Now, we found that many of these oxygen vacancies can be tracked optically by an optical absorbance, which is probably an electroabsorbance signal near the optical band gap. And so, for example, Shababa has been studying in detail the kinetics of charge trapping and charge transport in these oxygen vacancies in bismuth vanadate. And you can just see some examples of sort of timescales of charge trapping and transport, which she's measured in her studies. Of course, these oxygen vacancies in their bulk are mainly occupied by electrons, and that's what makes the system N-type. But in the space charge layer, these oxygen vacancies are largely vacant. They are largely released of their electrons, so oxidized, which is what causes the space charge, which causes the band bending, which means that in the bulk, these states are hole traps because they're full of electrons. On the surface, the same states act as electron traps because they're empty of electrons. As another example, tungsten oxide is particularly prone to oxygen vacancies. And this is just a study showing, for example, that if you vary the annealing time in air, and so in this case we are removing oxygen vacancies by annealing in an oxygen environment, then what you can see is that as you decrease the oxygen vacancy content, then the kinetics of getting the electrons out of the system gets faster. And indeed, what we've observed in a rather more detailed study is that if you vary the oxygen density in tungsten oxide, then there's actually, at least in terms of these sort of nanoneedle tungsten oxide photoanodes, there's an optimum oxygen vacancy density, which is neither too high or too low. And so the yellow curve here corresponds to an intermediate oxygen vacancy density compared to the two extremes. And we can see that directly in the kinetics, that we get more efficient charge extraction, and indeed longer lived carriers in the presence of a medium concentration of oxygen vacancies. And that's just one illustration of how the idea that defects aren't always a bad thing in some of these materials. As another example, here's carbon nitride. That's also a very interesting material for as a photocatalyst for water splitting. But it's a material based upon these rings. It's typically synthesized from urea, and that synthesis typically leaves behind urea defects. What we've observed in our spectroscopic studies is that these materials are full of these urea defects, and these urea defects function as deep electron traps. We can see that because if we look at the optical signal here, the decay of carriers, that's the decay of a carrier, and it's short. And the carriers live a long time. But if we look at the equilibrium between those carriers and the emissive states where they came from, then the emission decays much faster. The way we understand that is that initially the carriers, many of the carriers are only shallowly trapped and are able to be in equilibrium with the emissive states and so can emit photons. But over time, the shallowly trapped carriers, this is after our pulsed excitation disappear, and we just get left with deeply trapped carriers. These deeply trapped carriers are entirely non-functional because they've lost so much energy they can't do anything. But if you change the synthesis of the urea or the carbon nitride, so not from urea but now from melanin, and you treat it on the surface, the defects are no longer urea defects but NCN defects. And these NCN defects function as shallow electron traps, and now the electrons are able to go on to drive the catalysis of proton reduction. And so you can trap electrons in this material for seconds and still use that to drive the reduction of protons to hydrogen. The only challenge here, of course, is that now you're starting to accumulate lots of electrons in the system, and these electrons themselves cause recombination, which is a study we've been looking at recently. The last thing I'm going to talk about in terms of intraband gap states relates to a particularly interesting material if we want to think about something which has the potential to be really low cost. It's these photocatalyst sheets developed by Durrant in Japan. So these are not photoanodes and photocathodes. These are sheets of a tandem structure based upon validators of donor, essentially as the oxidation system, operating in tandem with strontium titanate as a reductant. And they've already been shown to be able to split water into hydrogen oxygen with a 1% solar to hydrogen efficiency. And they're remarkably cheap. Essentially, you can screen print them. The interesting thing here, of course, is there's no applied potential. It's just light. And these systems, because it's working as one unit, have to work with a single Fermi level. And so you need the Fermi level in the system is the same for both the oxidant, the oxidizing system, and the reducing system. And that's been puzzling us. And we wanted to understand that. And in particular, we wanted to understand why you have to both lanthanum and rhodium co-dope with strontium titanate to make it work. And so we did a study spectroscopically looking at this lanthanum and rhodium doped strontium titanate deposited as you can see a rather disordered photocathode on a gold substrate. Now what you can see is that the doping with the rhodium and the lanthanum changes the color of the strontium titanate. Strontium titanate's white. It's a wide bandgap semiconductor. It's not much use for absorbing photons. When you dope it with rhodium, it becomes very strongly pigmented. But this strongly pigmented strontium titanate is rather non-functional in terms of being able to split water. But if you reduce that rhodium, you can reduce it either with hydrogen or by co-doping with lanthanum. You end up with something which is still colored, not as strongly as rhodium, but which is far more functional. So you lose coloration, but you gain function. And we wanted to understand why that was. And the essence is that co-doping of lanthanum makes it much easier to generate the long-lived electrons, which in this case are going to be driving protons to molecular hydrogen. And so here's some optical data where we're looking on the seconds time scale now, LED on, then light off, and you can see the accumulation of electrons in the strontium titanate as a function of applied potential. And what you can see is you have to apply a potential near zero versus RHE, so quite a cathodic potential, to get a lot of long-lived electrons accumulating in the strontium titanate. But rather in contrast, when you lanthanum dope it, you can apply a potential of plus 0.9 volts and still have lots of long-lived electrons. You can see the plot of that here. So this is the long-lived electron signal versus voltage. And you can see, but when you've got the lanthanum co-doping, you can generate long-lived electrons even when you apply a positive potential to the material. And that's quite surprising because you'd imagine to drive a reduction process, you want to apply a negative potential. But this is able to work as a reduction system at plus 1 volt. And that's why the system works. The lanthanum doping takes out these rhodium 4+ states, which are the recombination centers in the system. And what that means is that we can generate long-lived electrons at positive potentials. Oops, sorry. And in particular, at positive potentials, where at the same potential, bismuth vanadate will oxidize water. And so the whole system is able to work at a positive potential to drive water oxidation. And it's also able to drive proton reduction at the same positive potential. And it's all about the ability of this lanthanum co-doping to make long-lived electrons without having to apply a potential to drive any charge separation, at least not such a strong one. So the last thing I'm going to talk about, I think I've got about another 10-15 minutes, Anna. I hope that's about right. Is to think about the kinetics of water oxidation. And a particular question which has been puzzling us has been that we know that to oxidize 2 molecules of water to 1 molecule of oxygen, you need 4 holes. And those 4 holes have in some way to come together to drive the chemistry of oxygen synthesis. And this, of course, is the challenge of the manganese cluster in photosystem 2, which accumulates 4 oxidizing equivalents to drive exactly this reaction. And we wanted to understand how these holes come together to drive that water oxidation. And so what we've been doing are what we call rate law analyses, which essentially is a measure of how the rate of reaction depends upon how many holes you have at the surface. Now, this is quite a controversial topic in electrochemistry. Almost all electrochemical kinetics are analysed according to a Butler-Volmer model. And the Butler-Volmer model essentially is a model developed for metals, which says as you apply a greater potential, then you lower the activation barrier to the resistance state. And so the rate constant for the reaction goes up. And so as you apply a potential, the rate constant gets bigger, and so the reaction gets faster. This was a model developed primarily to describe electrochemistry on metal surfaces. There's an alternative model which has been particularly developed by Nate Lewis, but it really comes from the thinking of Gershus at some time before, which is the idea that if you have a semiconductor and you apply a more positive potential, the main thing which happens is that the Fermi level approaches the band edge, and so the density of charge goes up. And so in this model, then there's no change in activation barrier in the simplest case, and so the rate constant stays the same, and what's changing is the population. And we've been, and most models so far, most analyses so far of kinetics of water oxidation have been applying the Butler-Volmer model. We were interested in thinking about whether a population model might work, and in particular whether a population model might help us understand how we bring 4 holes together to drive the kinetics of water oxidation. Now, in order to measure this, it turns out it's actually rather easy to do spectroscopy to measure these kinetics. And here's an example, actually not of a light-driven reaction, but water oxidation on nickel oxyhydroxide electrocatalysts, which is a very interesting material for electrolysis for water oxidation. If you put your sample in a spectral electrochemical cell, then you can measure the spectrum of the sample. And this can just be a UV-vis spectrometer and a potentiostat, and you apply a positive potential. What you observe for this nickel oxyhydroxide is as you apply a more positive potential, you see the appearance of an absorption band at around 600 nanometers. And this is the oxidation of nickel states to nickel, most likely nickel 4, and this potential range is the potential range of where water oxidation turns on in this material. And so we can use this as a measure of the density of these states. This sort of spectral electrochemical approach using optical data is very similar to an approach which has been recently developed within CINE, as I've been very pleased to see. But in this case, here we're using infrared spectroscopy to look at some of the states involved, looking in more detail at the molecular nature of the states, in this case, on hematite surfaces with a cobalt co-catalyst. Infrared spectroscopy has more information on the nature of the states, but it's harder to quantify charge densities. In terms of optical spectroscopy, it's well understood that if you've got an optical signal, you could turn it to a population by applying the Beer-Lambert law. And if you measure the current density, which corresponds to water oxidation at the same time, you can plot the current density, the water oxidation flux, versus the density of charges driving that current. And in this case, this is a log-log plot. The gradient is 4, which means that as you, every time you double the amount of nickel 4+ in the system, the rate of reaction goes up by 2 to the power 4, by 16. And so this is the idea. This then gives us the information that on nickel oxyhydroxide, water oxidation is 4th order in nickel 4+ ions and allows us to calculate a rate constant for that 4th order reaction. And it's a rather funny number of funny units because we're not normally used to thinking about 4th order reactions. Sorry, there we go. That was for dark reactions. We can do the same with light. In this case, typically we don't change the potential, we change the light intensity to change the density of holes. We can measure the density of the holes optically again, and this is the optical signal of the holes on the surface as a function of light intensity. Here's the current going. These are measurements done no longer in a simple UV vis spectrometer, but in one of our transient systems. But again, we can plot the density of holes on the surface versus the current density, which we measure for water oxidation, and we plot one against the other. And what we observe in this case is that at low hole densities, the flux of water oxidation is 1st order in hole density, which means essentially that the reaction of holes of water at low densities of holes, each hole reacts individually with water, most obviously to make hydroxyl radicals. But at high hole densities, the reaction goes up as the 3rd order in hole density, which as a number is rather surprising to us. We hadn't expected to see a 3rd order reaction. And so this is saying that every time you double the density of holes on the surface, the flux of water oxidation goes up as 2 to the power cubed, or 8 times faster. So this idea, I'll come back to. I'll come back to what that 3rd order means and why it might be 3rd order in just a minute. But this idea we can use optical data like this to measure kinetics of reaction is something which turns out to be quite generic. And so we've looked at it for proton reduction on ruthenium oxide. It turns out that proton reduction on ruthenium oxide is 2nd order in the 2nd reduction of ruthenium oxide, and that allows us to suggest the reaction is a homolytic reaction pathway. We can apply the same thing when looking at methanol oxidation on hematite. It turns out methanol oxidation is 2nd order in surface hole density, and that allowed us to propose a particular mechanism for methanol oxidation on hematite. As I've just discussed, we observe that water oxidation on nickel iron oxyhydroxides is typically 4th order in terms of hole density. It turns out some of these orders are pH dependent. I won't have time to go into it today, but it looks like reaction mechanisms depend upon the details of the electrolyte environment and indeed how you make your material. When we come back to the water oxidation on hematite, which maybe is the most classic system we've studied, then what we observed, as we said, was that the kinetics, so if you plot it now as turnover frequency versus hole density, increase as we increase the hole density from about 0.1 to 5 per second. We should note these hole densities are large, so we're talking about 1 hole per square nanometer as being the point at which you change mechanism of reaction. This corresponds to approximately when you start to oxidize nearest neighbor metal centers, which is maybe why you start to see a transition from individual holes reacting in this regime where the holes don't see each other to this regime where holes start to find they've got nearest neighbors. What we observe as we increase the density of holes at the surface, we just see more of these states. And so what that suggests is that the only thing we are observing are these holes, and it suggests that the rate determining step, I'm sorry, this thing always gets in the way. Oh, there, let's go. The rate determining step requires 3 holes to come together to oxidize what we believe to be a dimer of metal centers to make the OO bond as a rate determining step, and then the final hole comes on to allow oxygen to be released. And so what we have, the idea is an equilibrium between these surface holes and the rate determining step, and as we increase the density of holes, the equilibrium shifts to the right hand side and the reaction accelerates. Just coming back to that Butler-Volmer versus population argument, these are 2 examples of plots which indicate we are indeed in a population rather than a Butler-Volmer where the population model is appropriate. So data on the left shows measurements of the kinetics of methanol or water oxidation, or the current density for methanol or water oxidation as a function of surface hole density for different applied potentials. And what you can see is that if you normalize the data to the same surface hole density, then essentially the kinetics are independent of potential, which suggests that changes in band bending at the surface, which is the essence of the Butler-Volmer picture, are not important in terms of determining the kinetics. Another way of looking at data here is these are plots of the rate constant for water oxidation measured for different applied potentials and different surface hole densities for both methanol oxidation and water oxidation. And essentially what we find is that we can measure a rate constant for methanol or water oxidation, which is independent of potential and surface hole density. They fit rather well to the simple third and second order rate laws. And that suggests to us that this population model is indeed an appropriate way of analysing the data and not from a far more widely applied Butler-Volmer analysis. To give you an example of how we can take that sort of study further, then a rather easy thing is we can change the temperature. And what we observe when we change the temperature, we measure the flux of water oxidation versus surface hole density. At low hole densities, the reaction accelerates. And we can apply an Arrhenius analysis, again, an activation barrier of about 0.3 electron volts. And that is probably the activation barrier for holes on hematite, one hole oxidizing OH minus to OH radical, to OH dot. But at high hole densities, when we observe a reaction becomes essentially temperature independent. The activation barrier comes down to only 60 millielectron volts. And so that's suggesting that at high hole densities, hematite is able to catalyze the free hole oxidation, the oxidation of water as a third order reaction with a much lower activation barrier. And so in this sense, the hematite is functioning as a true catalyst for water oxidation. Now, this sort of data can be put together by theorists such as Victor Batista, who proposed a particular mechanism whereby the surface of hematite with no defects, this is just a planar slab of a 110 surface of hematite, can catalyze the free hole oxidation of water. I'm not going to go into the details, and indeed the details are not really the point and may not be the final story in the water oxidation mechanism. But the point is that what he was able to show was that the surface of hematite can enable three holes to come together in three different oxidations, where each oxidation step is essentially at the same potential. So this is the redox leveling, which, for example, we see in the manganese cluster of PS2, to achieve the three holes coming together, and then the final reaction to drive the water oxidation is at a rather small activation barrier, which are consistent with our data. And indeed, this sort of model fits not just our temperature dependence, but our pH dependence, and when we do kinetic isotope effect labeling measurements on the rate constant. And the nice thing here is that the model which he's used, I'm sorry, you can't quite see it, sorry, is a molecular scale viewpoint. So this is the model applied here is the same model used to describe water oxidation in the manganese cluster of PS2. It's different from the models typically used to describe catalysis on metal surfaces. It's a localized model around localized states. And the simple model is the idea that three holes have to come together, and the rate determining step is this oxidation, is OO bond formation, which requires three holes to come together on two metal centers to drive the reaction. So I think I need to stop there. I hope I've given you some thoughts both about the motivation for why you might want to make fuels from sunlight, some of the materials which are interesting, the kinetic challenge, and the challenge of trying to match excited lifetimes to catalytic timescales, and also at the end, the idea that spectral electrochemistry can provide remarkably simple insights into reactor kinetics, at least for materials where the states involved are colored. I've shown you the faces and names of many people involved in this work as I went through the talk, but of course I need to thank my research group, and particularly my solar fuels team, for all the work which I've been talking about, both our current and our past members, and the many collaborators we have, whom we're greatly indebted both for the materials and indeed some of the modeling and some of the other analyses, such as the XPS analysis, and of course our funders for making this all possible. I should mention rather wonderful journal, which you might like to submit your papers to. And I will finish with leaving you with a summary of my conclusions. Thank you very much. I hope that was interesting.
Thank you, James, for this very inspiring talk. So we are now open for questions. I ask you to type your questions on our YouTube channel so we can read it. We can please don't forget to type also your name in the name of your institution. Okay. I'll start with some questions. There's some anonymous question here for me as well. But James, in this last model that we're using, how you can decouple, because if you're applying voltage, it means if you're applying positive voltage in order to minimize the charge recombination, you are also accumulating holes. So how you can decouple these two things? Because with positive voltage, of course, you are going to accumulate holes.
Absolutely. And so, that's not what I wanted to do, was it? If I take that away for now.
In the last model.
Yeah. So this is data here where we were showing that the potential didn't matter as long as we normalize to the same density of surface holes. And so if I take the pale and the dark points here, the dark points here are that strong positive potential. In this case, you don't need much light to generate lots of charge. And so in this case, this point down here, this is quite a low light intensity of that potential. At 0 volts, you need much more light because you can't separate the charge so easily. And so that point there would correspond to a high light intensity at the same potential. And the point is that when you normalize to the amount of holes you ended up at, you get exactly the same flux of water oxidation. And so what we are concluding is that whilst, of course, having more applied potential helps separate the charge, so you need less photons to generate a certain hole density at the surface. The potential itself doesn't change the catalysis. So the potential is changing the charge separation, but it's not changing the catalysis. Does that make sense?
Yeah.
No, I don't want to do that.
Thank you. I have another question here. It's comparing hematite with bismuth vanadate. Hematite has much faster charge recombination and much slow kinetics. But since that the hematite performs better than bismuth vanadate, this is just because of the band gap?
So hematite absorbs more photons than bismuth vanadate. But actually, I think the highest performance is now with bismuth vanadate.
Is bismuth vanadate?
Yes, as far as I'm aware, at least as high or better than hematite. And I think the reason there is even though it absorbs less photons, the kinetic challenge is smaller. Mm-hmm. And so it's easier to generate to use the generated the charges generated by photon absorption to drive the catalysis.
Okay. Another question here. I saw your recent paper on carbon quantum dots for CO2 reduction. Okay.
Oh,
so
yes.
We had this conversation a long time ago about what do you think about, for instance, carbon-based materials, like for instance graphene. Can you comment on the whole of this graphene, carbon quantum dots on not only for CO2 photo reduction, but also for water splitting? What do you think?
So traditionally, people had focused on oxides and inorganics for water splitting. It's now obvious that there are many examples of carbon-based materials which are interesting for photocatalytic water splitting. Carbon nitrides is by far the most widely studied. Carbon quantum dots are becoming more interesting, and conjugated polymers are now starting to become looking very promising as photocatalytic materials. I think it's important to make a distinction between materials which are metallic versus materials which are semiconducting. So if you want, the light absorber needs to be a semiconductor material, because you need a band gap to generate electrons and holes, which are separated by an energy to give you lifetime and to store energy. Graphene is not, as far as I can understand, is not useful as a light absorber, but can be useful as a charge transport layer. And indeed, I don't think I mentioned that. If I go back, in one of the examples I think I had with, was it there? Oh no, I didn't have it down. So we have examples. Not there. Sorry. We have examples where using graphene can accelerate charge transport away from a semiconductor towards catalytic sites.
Okay. I think we have here one more question. Going back to your first slides about artificial photosynthesis, okay? So the PS2 is based on the catalyst with manganese and calcium. This is a very general question, like why you don't see many catalysts based on manganese in artificial photosynthesis? What's the problem with manganese?
I'm no expert, but my understanding is that manganese-based catalysts are less stable. The manganese cluster in plants has a half-life under operation of 30 minutes, and plants use 10% of all the energy they receive from the sun to rebuild the photosystem and put back the manganese after that degradation. There are examples of manganese-based inorganic catalysts for oxidation, but as far as I've understood, those they are particularly labile and are less stable compared to catalysts based on cobalt or nickel and iron.
So which are the best catalysts now at the moment for the water splitting?
Expensive ones. Things like, it depends if you want to go to acid or alkali conditions, but things like iridium or platinum are very good catalysts, but are less ideal for obvious reasons.
So as you know, our center here is supported by FAPESP, São Paulo Science Foundation, and also in Shell. So what you can tell for us, because we are developing materials, we're developing catalysts for water splitting and also for CO2 photoreduction. How far we are from a system, a photoelectrochemical cell that can actually drive water splitting and generate the green hydrogen. How far we are from this at the moment?
Well, there's already demonstrators at 100-meter scale in Japan, based upon these photocatalyst sheets from Durrant. And these are low cost, but not yet efficient enough to be commercially useful. There are other examples of systems which can split water into hydrogen and oxygen at efficiencies which would be commercially useful, but are either too stable or too expensive. There's indeed the Artificial Photosynthesis Center in Korea has a rather nice example of what they call the artificial cacti, which are taking CO2 from the atmosphere and using sunlight to make hydrocarbon-based fuels. So all of those things are already happening. How long until we get to something which has all the attributes required for commercial application? If you believe Professor Doman, he would say quite soon. I'm probably more cautious, and I would guess still a few years for the first application.
Okay, you have our online question for Professor Pablo Fernandes from the Chemistry Institute at Unicamp. Can you read it, James?
I can read it, that's fine. So some people are great fans of hematite. Yeah. And it's clearly a very interesting material, but and as I talked about, the stability and the energetics and the cost all in its favor, but it's hard because of the kinetic challenge. my own group's research has focused a lot on hematite because it's such a fantastic model system to study. But we have samples from Michael Gratzel, which we received 5 years ago, and we're still studying because it's so stable. And that makes it very easy for us to do really detailed, consistent spectroscopy. And so our own motivation for studying hematite is because it's a really useful model system to study the challenge of trying to get these photoanodes to work. Whether really it's going to be the most useful one or not, I don't know. That's for material scientists to answer.
I have another question from Eduardo. Eduardo is a postdoc in my group.
Ah, yes. I can't see the question. I can only see the start of the question.
Is
yes. Yeah. So this is about the how to analyze the Butler-Volmer behavior and the symmetry factor. So the whole idea behind that analysis. There's my picture on that. Is the idea that as you apply a potential, you reduce the activation barrier to a reaction. And the scaling factor or symmetry factor, which you refer to, refers to how much potential do you have to apply to reduce the activation barrier by a certain amount. And a symmetry factor of 1/2 means you have to apply 100 millivolts to reduce the barrier by 50 millivolts. The analysis we are using is assuming that as you change the potential, there is no change in activation barrier. And the evidence for that is that as we change the potential, the rate constant doesn't change in our measurements. Now, that is bound not to be generally true. The analysis we are doing is, if you like, the extreme of assuming that we only have to think about population and not at all about changes in activation barrier. So far, it's worked quite well to analyze the data we have on the materials we've studied under the conditions we've studied. How generally relevant it is and at what point we have to consider both changes in population and changes in activation barrier, I think will depend upon the conditions we use. This relates to the idea of whether we're in the limit of Fermi level pinning in the more technical language. That is a question of how widely applicable this population model is, and indeed how well we really can apply it to electrocatalysts as well as to semiconductor photoelectrocatalysts is, I would say, still quite an open question.
Okay. If you are no further questions, there is one more question here. From Juliana Ferreira de Brito. What's your opinion about join? Okay, here. It's on display.
Yeah, that's fine. So if I could, absolutely interesting. So this is a question about should we be going beyond water splitting, either to reducing CO2 or to oxidizing something else. So reducing CO2, of course, is interesting. It's also hard. The catalysis of CO2 reduction is challenging. I gave you one brief example of that with those the reduction of CO2 on titanium with silver particles. I didn't mention the quantum yield, which was tiny. But clearly the idea of driving either CO2 reduction or maybe even more challenging nitrogen reduction would be interesting. Rather more promising, I would say, is the opportunity for oxidizing organics. So making hydrogen on one side, but not oxidizing water, but oxidizing organic. And so this, we had one example, I gave you one example where we're oxidizing methanol to methanal on the surface of hematite. And that was actually pretty much 100% quantum efficiency, Faradaic efficiency for making methanal from methanol. And the nice thing there is, if you're making something which has got a reasonable market, it's got a value, methanal is more valuable than methanol, and it was easier than oxidizing water, so it would need less potential. And so the idea of oxidizing something easier than water is certainly a good idea. In Brazil, I would have thought glycerol oxidation is particularly interesting. Indeed, we're starting to look at the challenge of glycerol oxidation, because, of course, glycerol is one of the waste products of the bioenergy industry. That, of course, is very interesting. It won't be as scalable as oxidizing water if you really want to power the planet, but in terms of trying to make some money in the shorter term, I think it's very sensible.
Thank you, James. We have a question from Professor André Formiga from the Chemistry Institute.
So this is about the acidity of OH sites on the surface, and that's quite hard to understand. So as I mentioned, as you oxidize the surface, then you accumulate a large amount of charged carriers, and these charged carriers drive these charged carriers themselves will tend to change the band bending. And so as you accumulate more charge on the surface, the space charge layer becomes less effective at keeping those holes safe from electrons in the bulk. But at the same time, there's quite a lot of indication that as you accumulate holes on the surface, there's proton release. And so one of the suggestions from the modeling by Victor Batista is that actually hole accumulation on the surface of hematite is charge neutral, which is why you're able to bring three holes together to oxidize water without having an activation barrier for the reaction, which essentially is the same idea as in plants, that the manganese cluster drives proton-coupled electron transfer, so that each oxidation releases a proton, and the cluster remains charge neutral on the surface during water oxidation. I'm not sure that fully answered your question. That's probably the best I can do.
Thank you, James. So we have the last question of the talk.
This one? There's a mismatch. Yeah. So this is an interesting thing, that as far as we can judge, the holes on the surface of hematite can oxidize water without any applied potential. You need an applied potential to get the holes to the surface, but once the holes are at the surface, then the kinetics of water oxidation are independent of potential. This is the same idea as when we measure the activation barrier for the reaction. It's almost activationless. And that does beg the question of why do you want to put catalysts on? And of course, the reason why hematite can oxidize water, or one of the reasons why it can oxidize water without a barrier, is because the valence band is so deep. And so these holes are effectively operating at a huge overpotential, because any hole on the surface of hematite is very deep in a deep valence band. Most catalysts work at much more modest potentials, and so are thermodynamically more efficient. And therefore, so the interesting thing is that if you put a catalyst on the surface, the holes go to the catalyst, at least in principle. That separates the charge, but you don't have to lose kinetics, because you're still able to drive the catalysis because the catalyst can work at a smaller overpotential. I'm not sure it answers your question, but it's how I would think about it.
So, thank you, James. I think I'm going to stop here. And again, thank you very much for this very inspiring talk. And James and I will have, we just approved a sprint project with a PESP. Unfortunately,
not much has happened so far.
we are planning. I was planning to visit James now in July, but I think we have to postpone for next year. But we hope to see you in our second annual meeting here in CINE next year. And
yes, I very much hope to get there. Yes, and I can see with some of what you're doing, and particularly some of the links with your synchrotron, give some really exciting opportunities for collaboration.
Yeah. So hope to see you soon in person. So again, James, thank you for this wonderful talk.
Thank you very much for the invitation and the chance to talk with you. Very good. And good luck with all the challenges you have with, as with everyone, with the challenges of the coronavirus and lockdown. You're able to progress. Very good. Thank you.
Thank you, and thank you everybody that was attending our webinar.
Very good. Bye bye. Thank you very much.